Good afternoon. My name is Nan Zhang, and I'm from Indiana University. The paper I'm going to present today is Leave Me Alone, App-Level Protection Against Runtime Information Gathering on Android. Don't know where's the controller. Oh, yes, over here. Sorry. As it is well known, Android system uses permission-based access control to protect its resources. An app only needs to specify the permissions it wants to use at installation stage, and then it can use the resources that the permission protects whenever it wants to. And also, sandboxing is used to separate those apps from each other in order to protect its private information. However, enormous attacks have been proposed to threaten such security mechanisms. For example, if a voice memo app is granted record audio permission, it could also use such capability to record a phone call where it can extract credit card information. When user interacts with a phone menu system, and that asks the user to either type in or speak the credit card number. And also, another example is that malicious app could installed on a phone could infer the routes the user is driving by leveraging the speaker usage of Google navigation. Also, the proc file system that inherited from Linux also exposed a lot of information of an app that could be used to infer sensitive data. For example, in this attack, the UI state of an app could be inferred through shared memory side channel, and thus enables a malicious app to hijack the UI state and steal sensitive user input or obtain sensitive carrier images shot by the user. So we define all such attacks that directly steal or indirectly infer sensitive user information at victims' app's runtime as runtime information gathering attacks, and RIG for short. So to successfully deliver a RIG attack, the malicious app needs to run side by side with victims' apps, collecting their data. A lot of researchers have proposed RIG attacks, and most of them are of high impact. And the new RIG attacks are continuously proposed every year in top conferences. Those attacks together are threatening 1 billion Android users. So while we look into IoT devices last summer, and we found that they are equally vulnerable to RIG attacks. The two devices we studied, which are Belkin Net Camera with night vision and Nest Protect, are among best IoT devices. In order to make use of a net camera, it connects to the internet via home router. The controller app on the phone will talk to the net camera either directly through home router or through public internet if the user is not at home. Whenever the net camera wants to send a message to the controller app, it will go through the net camera server, and then the message forwarded to the Google Cloud Messaging, and finally the message will push to the user's phone. With the model in mind, two side channel could be utilized to infer information of IoT devices, and enable 3 attacks that could make a burglar break into a nobody home without being caught at scene. So let me elaborate each attack one by one. There is a function called motion detection in net camera that enables the camera to record video if the image it captures has changed, and raise alarm to the user. However, if the user enables this function, it also means that she's not at home, because otherwise the motion detection will generate lots of alarms. So a malicious app installed on the phone could infer such information through the traffic statistics side channel. And then if an alarm is raised, it will be passed to the GCM server and then to the GCM process on the phone. The GCM process will deliver the alarm to the net camera app. This could be also inferred through a fixed length range of traffic statistics of GCM process, and then observed that net camera will use CPU immediately after this. So once the malicious app got such information, it can mute the alarm, mute the phone, and make the alarm less noticeable to the user. In the end, if the user is watching live video or viewing clips recorded by motion detection, a lot of traffic will be introduced. And the malicious app could easily infer this information and notify the burglar to run away right before the police comes. Also, the Nest camera also shares the same vulnerability of mute alarm attack that could make it useless in reporting alarm that there's a bad situation happening in the user's home. So given the pervasiveness of rig attacks, what should we do to protect those victim apps? We have proposed app-level protection, App Guardian, and Guardian for short, to defend against rig attacks. Guardian prevents apps running while the principal app is running, and it has low impact on system performance and other apps utilities. So due to the fragmentation of Android, a framework solution might not be might take forever to deliver to distribute it to the users. On the other hand, pushing this problem to the app developer is also not a good idea, as it is less clear what an app developer could do to control its information exposed by the operating system. So if we can achieve this goal at app level, users will get immediate protection against rig attacks. As you can see, the Guardian app has three components: a monitor, a detector, and a controller, as shown in the center of the green box. Whenever the principal app is running, Guardian uses a set of security requirements retrieved from Guardian server, and also scan other apps' information in its monitor module. Then the detector will analyze the results and based on the security policies to find out suspects. And the controller will suspend those suspicious apps and restore them after the principal app has finished its job. So in the perspective of Guardian protection for a single principal app, the Guardian will enter a mode called ward mode when Guardian detects the principal app is running. And within this mode, the Guardian suspends all suspicious background apps. Only after the principal app finishes its jobs will Guardian exit the ward mode. And will further clean the public information left behind to ensure that no malicious app will get useful information. Then the suspended apps will be restored by the controller component. So the app states are well preserved when closing, and the majority of those apps are marked as disposable by Android system when low memory occurs. As most memory clean tools will also close such apps. However, it still takes a longer time to restart an app than to switch it from background to foreground. So finding the right suspects becomes a key issue of App Guardian. In our research, we use malicious app side channel to infer their malicious behavior and only suspend those apps with malicious behaviors. Like in data stealing attacks, record audio permission is granted to an app. When it starts to record audio, the media recorder process will spawn a new thread called audio in X, where X is the number, and on behalf of the app to record audio. This could be found directly through the proc file system. However, if a phone call is ongoing and at the same time the app is recording an audio, it will be a problem unless the user consents to do so. So such behavior should be stopped immediately. And in side channel attacks, we had observation that the malicious app needs to sample principal app at a very high speed, high enough to capture fleeting events. We look into the CPU usage of the app, and we found that such action will cause the kernel time to increase, but the result is very rough. So we further look into the scheduling statistics of each thread in this process. And we found that every time the malicious app samples principal app, its number of times scheduled to use CPU will increase. And we will use this two-side channel to find malicious behaviors. And one obvious situation is that if an app only runs when the principal app is running, it is highly likely that it is a malicious app that's stalking the principal app. By calculating the Pearson correlation coefficient, 4 times of such behavior are enough to identify their correlation. A malicious app could also play a trick that it uses multiple apps to sample the principal app, with each of them at a lower speed, but combined together could infer some useful information from the principal app. In order to defeat this, App Guardian will automatically group those apps with same signature or their installation triggered by another malicious app. And malicious app could also make the link less obvious by recommend another app using a website or email. So we will, in this case, we will ask user for their relation. And Guardian app also needs to protect itself being killed by other apps. To achieve this purpose, App Guardian will use Start Foreground to start its service as a foreground service. In this case, it cannot be killed by any other apps. The malicious app could also play the same trick. And in our experiment, we found that 7 apps out of 475 apps from Google Play have such capability. However, they will no longer be stealthy because the notification, as shown in the picture, will always be displayed in the notification center, and it cannot be removed. So in this case, even if they indeed have malicious behaviors, a user will be suggested to close such apps manually. And we first test App Guardian's effectiveness against all known rig attacks at that time, and found that such attacks could all rig attacks could be defeated. If a malicious app runs at a lower speed in order to circumvent the protection provided by App Guardian, it will not be able to gain enough information to make the attack happen, and their successful rate will close to a random guess. For example, in the Google navigation attack, if a sampling rate drops from 100 times per second to only once per second, its successful rate will drop directly through 78% to only 6%. We also evaluate the App Guardian on the impact of its system performance and utility impacts, and collected on 27 categories in Google Play for 475 popular apps. We found that 92 of them potentially needs to be closed, but only 8 of them have utility impacts and may further affect the user experience. We further measured the overhead introduced by Guardian app on 2 Nexus phones with 250 apps installed on each phone. And within the world mode, 5% of CPU and 40 megabytes of memory is consumed by Guardian app. And if it is out of world mode, only less than 1% of CPU will be used. For battery usage, we tested on that 2 Nexus phones, but only with 50 apps installed on each device, as it is a more realistic number of apps people usually have on their phone. So on average, the estimation shows that only 1% of total battery capacity will consumed per day. So far, we have proved Guardian can defeat rig attacks at lower cost. Some future works could also be done to better protect Android from rig attacks. Firstly, App Guardian is not a malware detection system. It could only suspend a small set of apps to protect principal apps. However, it does cause some utility impact and inconvenience. So more accurate identification of malicious behaviors will certainly help. Currently, Guardian will consume more resources to protect background system services, as there's no entry point or exit point for such apps. how to protect them at a minimum cost is a challenge. The last thing to mention is that Guardian could clean public information of a principal app when it finishes its jobs. However, traffic statistic data is left behind because only a phone reboot will make it clean. In conclusion, we identified the seriousness of rig attacks and demonstrate that IoT devices are equally vulnerable to rig attacks. We are the first one to propose an app-level protection, App Guardian, that only has normal privileges and uses side channel to protect apps from rig attacks. And we will release the app and the code once it is mature. We believe that our techniques significantly raise the bar for rig attacks. Now, new attacks discovered will be put into the test of this defense to make the case that they indeed pose a realistic attack. And this paper further inspired follow-up effort on an app-level protection against security threats on mobile devices. And thank you all for listening. Any questions?
Hi, Sven Bogil, Saarland University. It seems your warden heavily relies on the proc file system to detect the stalking apps.
Yes. And
the techniques you apply somehow resemble what you do in a reconnaissance phase before mounting, for example, root exploits. And for example, projects like SE Android propose that security policies should be enforced that an application can actually not read the proc entries of other applications. So I'm wondering, did you consider, besides proc file systems, some other side channels to use in your warden?
Yes, actually, we have looked into a lot of side channels that we could collect it against those malicious apps. There's no general way for those side channel attacks or rig attacks to use their side channel against victim apps. So we found that only their CPU usage will be obvious observation to find their malicious behaviors. But we'll definitely consider more side channels to find their malicious behaviors.
Okay, thanks.
Thank you.